Perfect. So it's a great pleasure to have Tom Hartman here today to tell us about islands in cosmology.
All right, it's great. Thank you very much. So I'm going to tell you about a recent paper with Yikun Jiang, who's a student at Cornell, and Edgar Shigulian, who was a postdoc at Cornell, has just moved to Penn. So the islands referred to in the title are quantum extremal islands. And quantum extremal islands have been a hot topic recently in the context of black holes because they've been realized to be an essential ingredient in understanding the entropy of Hawking radiation. So this came of looking at the entropy of radiation to try to understand the information paradox. So let me describe the regions here. So this is a Penrose diagram for an evaporating black hole. There's Hawking radiation, which are these little squiggles coming out of the black hole. And the setup is one where we want to calculate the entropy of this region labeled R. R for radiation in this case. I'm going to keep using R throughout the talk, although it's not necessarily going to be the radiation. It's just going to be whatever system, whoever's entropy we want to calculate, I'm going to call it R. So in this black hole context, what's been found is that there's a formula for the entropy, which is this formula showing up here, called the island rule. And the idea is the following. First, you include a region I for island, in the black hole interior. So that's this region over on the left. You include a region I. You calculate the generalized entropy of I union R. So this is the formula. We calculate the generalized entropy of I union R. So that's the area of the island. You can think of that as the area of the black hole horizon, which is basically what this ends up being for the evaporating black hole. So there's an area term, and then there's a second term, which is the entropy of matter fields. In this case, it's the entropy of, so this is the von Neumann entropy of matter fields on the joint region I union R. Now, what happens in the black hole case is that you have, let's see, so my Hawking quanta have gotten sort of obscured here, but we have all these Hawking quanta going out, and those have some interior Hawking quanta inside the black hole on the left when they're entangled with each other. So if we were to look at just one of these individually, it would have a very large entropy. So like if we wait for the black hole to evaporate, then we have all these Hawking quanta going out. So there's a big entropy in that Hawking radiation. But if we also include region I, then we not only have the Hawking radiation, we also have the entangled partners of the Hawking radiation. And so that combination is very small, the quantum field theory entropy of I union R. So SQFT just means the von Neumann entropy as calculated using the ordinary techniques of quantum field theory in curved space. So the story for black holes is that well, first of all, there's a Euclidean path integral argument that this really is the correct answer for the von Neumann entropy of the black hole. And furthermore, this region I does show up and alters the final answer for the entropy of the Hawking radiation. Particularly, it shows up when it shows up at late times when the entropy of the Hawking radiation is large and starting to be in tension with unitarity. So basically the name of the game of this talk is going to be to look for other situations where an effect like this can potentially occur. A few comments I want to make about the black hole case. First of all, this isn't just a trick for calculating the entropy. Well, it's partly that. It's partly a formula for the entropy, but it's more than that because there's a proposal with quite a bit of evidence that when you have an island like this, not only does it contribute to the entropy, the whole region is encoded in the quantum state of the matter in region R. So this is sort of like a holographic duality, although I put it in quotes because it's, well, it doesn't necessarily involve a reduction in the number of space-time dimensions. So it's not necessarily holographic. So in this case, if we had a four-dimensional black hole, then we would say that the interior of this four-dimensional black hole is encoded in the state of the Hawking radiation, which is a four-dimensional quantum field theory. This is not holographic in the sense of reducing the space-time dimension. But other than that, it's really very similar to ADS-CFT in that it's encoding of a gravitational state in a dual system where gravity is not important. In this case, the Hawking radiation far from the black hole is like the dual system. So it's a holographic duality in the same sense as subregion duality in ADS-CFT. Now, the appearance of the island relies crucially on two things. The first is that the generalized entropy has to have an extremum. So if we go back to the this island formula for the entropy, then the island formula says that we're supposed to extremize the generalized entropy. So that's, we're extremizing over all choices of island. So there has to be an extremum. If there's no extremum, then the island is just trivial. It's just the nothing region. In other words, there is no island. So there has to be an extremum. The second crucial thing to get this effect is that there has to be lots of matter entanglement between region I and region R. The reason for that is that we always have the option of not including an island at all. So, and this goes in the formula, this is because this minimum. So what we're supposed to do is to consider all possible extrema and then pick the one with the smallest entropy. So we can always just pick the nothing island on the right here. If we want to get a non-trivial island, then we need it to dominate the entropy. In other words, we need the entropy involving an island to be less than the entropy calculated without the island. In the derivation of the island rule, this comes down to calculating contributions to the Euclidean path integral and picking the one that dominates in the Euclidean path integral, which is the one with smallest entropy. In the example of the black hole, this large entropy, this large entanglement between region R and region I is provided by the Hawking radiation. So, of course, we said the black hole is evaporating. At late times, when this island appears, it's appearing because there's a great deal of entanglement between the two regions. Why does that help? Well, as I was saying before, when we look at this generalized entropy, that doesn't count matter that's entangled between I and R, because that matter is pure from the point of view of the combined region I union R. Okay, so I went through that sort of quick because I think people have seen this. Are there any questions about the black hole setup before I continue?
Yeah, just one question, Tom.
Yeah.
You described the island formula as kind of like holographic duality. And I was just wondering, is there a concrete argument why entanglement wedge reconstruction should work for the island formula in the same way that it does in ADS-CFT?
Yeah, there's an argument for that, which is very similar to the argument that's been given in ADS-CFT, which is basically that, well, I don't think the details have been worked out. The way the argument goes is basically that if you can get the relative entropy, there's an information-theoretic statement that if you get the right relative entropy, then you can basically reconstruct the state. I think that would more or less go through in this case, although I'm not sure that anybody's really worked out the complete argument here.
I see. Okay, thanks.
Okay, so what I want to do here is I want to ask the question, other than evaporating black holes, when else do islands appear? For a perhaps provocative example, can we make an island telephone? And what is an island telephone? So we just said that you can encode, you can access a region, a distant region in space-time, can be accessed if you have a lot of entanglement with that region. So can we do the following? Can we, as an experimenter sitting on Earth, create a bunch of bell pairs, then send half of our bell pairs on a spaceship to Alpha Centauri, and then carefully arrange those entangled pairs in a way that produces an island and allows us to access the quantum state out at Alpha Centauri? Okay, that sounds crazy. Surely this is impossible. It can't possibly be that easy. There has to
Tom,
be
I was going to say the other way. Isn't this like an obvious consequence of the ER equals EPR type arguments?
Well, in ER equals EPR, it's really a different statement. In ER equals EPR, the statement is that if you collapsed these two sets of bits into a black hole, then you'd have a geometric wormhole in the middle joining them. If you could make an island telephone, you could do something much stronger, which is that you could basically act with your quantum computer on the bits in your lab, and you could access the operator algebra out at Alpha Centauri. So I think this is a stronger statement, and we could probably cook up paradoxes that this would produce. So it sounds a little crazy. I'm just mentioning it because from the island rule itself, it's not obvious that this would be impossible, right? If we have lots of entanglement, maybe we can arrange things that we could get an extremum. Maybe we could do things like this, but I'm going to prove that this is not possible. You can't build an island telephone. Secondly, cosmology also has lots of entropy production. So this seems like a natural place to look. Does cosmology produce islands? The bigger underlying question here is, does this provide a handle on holography beyond ADS-CFT, as I've sort of been suggesting? So the answers here are going to be, are there an island telephone? No, there's no island telephone. We're going to understand exactly why that's impossible, what prevents it. In the process, we're going to derive some general constraints on when islands can appear, what sorts of spacetimes we expect them in. Cosmology, does that produce islands? The answer is sometimes, and I'll discuss examples. Does this provide a handle on holography beyond ADS-CFT? Well, that's something I won't get into very much in this talk. I think the answer is clearly yes, to some extent, but this is really sort of, I hope, early in this exploration, and I think there's a lot still to be understood about exactly how far we can push this. So the plan is to first discuss general properties of islands, and I'm going to discuss 3 general conditions that are necessary for islands to appear. Then, so that'll be just a general discussion in general spacetimes, and then I'll talk about applications to FRW cosmologies. So the first condition is going to be related to the Beckenstein area bound. So the holographic principle suggests something like the Beckenstein area bound, which I've written here in quotes, as the entropy of a region being bounded by its area over 4 in Planck units. Now, this is in quotes because we have to carefully define both sides. We have to say what we mean by the entropy. If this were the von Neumann entropy, it would be infinite. The area gets renormalized. So we have to be careful what we mean by this inequality. But at least for spatial regions, this equality is not true. In fact, the fact that this equality is not true is one of the main things that led Busso to the Busso bound, which is a version of this inequality that is true. But just this equality, as stated, has counterexamples. It's I think the most famous counterexamples are, first of all, the black hole interior. In this case, the entropy of the interior grows as the black hole evaporates, whereas the entropy of the horizon shrinks. So eventually that area term is going to zero while the entropy term is getting large. So clearly this is being violated in the interior of a late time black hole. Secondly, it's violated in cosmology. So this is also very easy to see. Consider the case where you have a Big Bang. And so you have a scale factor A of t that's going to zero at some time zero. Well, then if we look at the entropy of a region, the entropy of a co-moving region in cosmology is constant because the evolution is adiabatic. So that entropy term is constant. Whereas if we go back to very early times near the Big Bang, the area term is going to zero. So either by taking regions that are very large, or by taking reasonable size regions and taking them very early in time, we can always violate the Beckenstein bound in cosmology. So let me state the first condition of these general conditions on islands. So condition number one is that the Beckenstein bound must be violated to get an island. So there's a precise version of this equation. I'm writing the almost precise version. The totally precise version will come in a minute. And the thing that makes, so let me say what the ingredients are here. So on the left-hand side of this inequality is the entropy of the island itself. So maybe I should step back a minute here and emphasize the point of view here. In the work on the black hole, they picked a region R. So the first step was to pick a region R, and the second step was to find its island by applying this rule. That is not really the philosophy that I'm following now. Now what I'm saying, we have some space-time. Can there be islands anywhere? I don't care what the region R is. I'm more interested in what the region I is. Like what's a region in space-time that itself can be someone else's island? So that's the question we're asking. And note that the conditions that I'm gonna state refer only to the island, and they don't refer to the region R that shows up in the island rule. So this is like, it's a bit like asking what kinds of space-times or regions in space-time can be encoded holographically. It's sort of like that question in the context of the island. So on the left-hand side, we have the entropy of the island. What this is the, I guess to be consistent with my notation here, I should have called this SQFT. So this is the finite part of the matter von Neumann entropy of the region I. It's important that it's the finite part, otherwise the left-hand side is infinity. On the right is the area of the region. There are corrections to this inequality, but they're subleading compared to the terms that are written. So this is maybe the simplest thing you might mean by the Beckenstein bound. You just take the non-infinite piece, subtract off the infinity in the von Neumann entropy, and then this is the Beckenstein bound. It's showing up as the matter entropy is larger than the area in order for it to be an island. So it's violating. I'm going to sketch the derivation of this to give a flavor. So it comes from the fact that the island, the entropy, well, remember we're looking for the dominant island or the dominant, the minimal entropy island. So we have to ask whether the island gives a smaller entropy than the no island possibility. If you write, if you compare these two calculations, so the island entropy has an area term from the area of the island. It has a quantum field theory term of I union R. And I didn't write this term earlier, but I should have to be careful here. So this is, so what this term is I'm subtracting off the UV divergence in the quantum field theory. You can think of this, so usually the way we think about this is that this UV divergence is absorbed into the renormalization of Newton's constant in the area term. So when we combine the first term, well, when we combine all three terms here, we get something finite because the renormalization of the first term cancels against this the UV divergences in the Q of T. On the right-hand side is just the no island calculation of the entropy. That's the one where you just ignore the island rule and you go back and you calculate entropy by the standard quantum field theory or quantum field theory and curve space formulas. You can rearrange terms a little bit here to rewrite this in terms of finite quantities. So in terms of finite quantities, I've just moved some terms around, but it's just the same inequality written in terms of things that are finite. So on the left is the generalized entropy of region I, of the island I. On the right is the mutual information of I with R, which is this combination of von Neumann entropies. I should say, by the way, that this fact that the Beckenstein bound has to be violated, if we had been dealing with a finite quantum system, then it would be, and it obeyed the island rule, then this inequality would be sort of obvious. Take my word for that, like if you were read this down for a tensor network or something, this inequality would be sort of obvious from the island rule. And the subtlety in deriving it in quantum field theory is dealing with the divergences. So if you just sort of follow your nose, then you'll get something that is trivial due to the divergences. So that's why we're going through this a little more carefully. In the next step, I'm going to replace region R by a bigger region, R prime. And according to strong subadditivity of the von Neumann entropy, the mutual information increases when you do that. If we increase the size of one of the regions, then SSA tells us that the mutual information also goes up. And we're almost there. So now what we're going to do is we're going to pick, so this is the setup of the island and region R in space. And what we're going to do is we're going to grow region R and apply strong subadditivity in this way. And we're going to grow it all the way until it's almost at region I. So region R prime is everything outside of the island, except for a little strip around it, which is going to act as a regulator. Now with a quick calculation, you can check that when you can check that the largest contribution to the mutual information in this situation where I and R prime are just separated by a tiny strip is actually just twice the finite part of the von Neumann entropy. This is sometimes called the mutual information regulator for entanglement entropy that was discussed in a paper a few years ago of Cassini, Huerta, Myers, and Yale. Now the generalized entropy on the left is just the area plus S of I. So if we subtract a finite S of I from each side, then we get area is less than the finite part of S of I, which is the claimed violation of the Beckenstein bound for islands. Okay, so I wanted to go through that just to I have a few of these conditions. That's the only one I'm going to do in detail like that, just to sketch the kind of ingredients that go in. Are there any questions?
Yeah, one small question. So you pulled out the ultraviolet divergence explicitly at the beginning. Do you also have to worry about infrared divergences, or are those not a problem? I have in mind the zero temperature situation that you discussed in your paper with Juan and Edgar and friends.
Ah, yeah. I think the answer is that no, the formulas are the same. There are situations where the infrared divergence makes this sort of always satisfied. So like if the thing on the right hand side is infinite, say your region I is a semi-infinite region in 1+1 dimensions, then this inequality is not very useful. It's just always satisfied, but it still holds in that case.
I see. Thanks.
Are there other questions? So this answers my question about island telephones. The answer is no, there cannot be island telephones. To be more precise, you also have to assume the Busso bound. So if you assume the Busso bound, then this Beckenstein condition tells you that it's impossible to engineer an island by sending entangled qubits to Alpha Centauri. So let me sketch that argument. Say we're the experimenters here, and we're going to try to send some qubits to Alpha Centauri while we stay in our lab. And then we're going to hope to produce an island at some later time that's very far away. Well, so region R in this case is our lab, and we're trying to open up a region R that's very far away by sending entanglement there. Well, the only way we can do that is if S qubits of I is greater than the area of di over 4. So we have to send an enormous number of qubits, first of all. But there's a problem with this, which is that if we try to send these qubits to region I, then those qubits will pass through a null surface. And the Busso bound tells you that the entropy flux, the classical entropy flux or hydrodynamic entropy flux through a null surface is bounded by the area. So it's impossible to send, it's impossible to violate the Beckenstein bound by sending matter through a null surface, because that would violate the Busso bound. So that's the argument. The conclusion is that the Beckenstein violation must be from something more subtle. You can't violate it just by sending a lot of entanglement somewhere. So for example, you can violate it by Hawking radiation. In Hawking radiation, the growth in entanglement between the inside of the black hole and the outside of the black hole, that growth in entanglement does not come from the flux of bits across the horizon. It comes from Hawking radiation, which does not involve any flux of physical bits across the horizon. So it has to come from something like that. You can't just engineer it. So you can't make an island telephone, unfortunately. So now, is a violation of Beckenstein's area bound enough to guarantee an island? That might be our next guess, is maybe if we violate the Beckenstein bound, maybe we always get an island in that situation. But no, it's not enough. To explain the other conditions, let me first define what is called a normal region. So classically, a region is called normal if it obeys these two conditions. So basically, it says that outward going light rays unfocus and inward going light rays focus. So a simple example of a normal region in flat space-time would be a circular region. If you have a circular region and you look at the ingoing light rays, they converge. So that's a normal thing to do. If you look at the outgoing light rays, they diverge. So that's a normal thing to do. So that's called a normal region. As opposed to like a trapped region, where both of these light rays would converge if you were in a trapped region. So that's a normal region. Now I can state condition 2, which was also observed in the paper of Almeri and collaborators in the context of JT gravity in 2 dimensions. So here's condition 2. It says the boundary of an island must be quantum normal. It must lie in a quantum normal region. So a classical normal region was a statement about the area. A quantum normal region is a statement about the generalized entropy. So a quantum normal region is a region where if you do an outward null deformation, the generalized entropy increases. If you do an inward null deformation, the generalized entropy decreases. I won't go through the derivation in detail, but it starts from writing the extremality equation for quantum extremal surfaces in this way, in terms of the mutual information, and then we invoke strong subadditivity in order to get this inequality. But let me skip the details there. So both of these conditions are conditions on the island. Let me emphasize again that they don't refer to region R, they just refer to the region I, where we're asking, can this be anyone's island? Condition 3 is similar. So here's condition 3. We take our putative island, our region I, that we're asking if it can be an island, and we draw a region around it, which is region G. It's sort of like the complement of region I, but it's only the complement kind of locally. It doesn't have to be the whole complement of region I. So condition 3 states that this region G, no matter what G you pick, must also be quantum normal.
Hi, Tom.
Yeah. Hi.
Can I ask a question about condition 2?
Sure.
So let's consider an evaporating black hole, and let's consider the positive null direction that's parallel to the horizon. Then the S matter, I would think that S matter would not change, because the deformation is sort of parallel to the Hawking radiation. And I would also think that the area of the quantum extremal surface would decrease because it's in the horizon. So what, am I missing something here?
Yeah, I think the crucial thing about the evaporating black hole is that the edge of the island. It's the fact that the quantum apparent horizon is actually inside the event horizon. The quantum apparent horizon is inside here, and if you find the island, it actually will appear between the event horizon and the quantum apparent horizon. So the fact that the apparent horizon is slightly inside is what gives you that leeway to move the island slightly inside.
Okay. So
sorry.
Could you clarify which one? So which one of the matter or the quantum extreme surface area would increase? Do they compete with one another? Can you clarify a little bit more?
Sorry, in which situation exactly?
In the evaporating black hole situation.
But under which deformation? The one that goes this way?
In the positive, yeah, that way.
The area term is decreasing.
Right.
So we need to pick the.
So matter has to increase.
Right.
Yeah.
I just had a quick question about condition 3.
Uh-huh.
So is there, if I make G larger, does the condition get stronger, or are all of these independent? Is there something like that?
Yeah, there is something like that. So if you make G larger, the condition gets stronger. However, and I was going to kind of gloss over this, by making G larger, you also restrict where your region R is allowed to be, because it has to be space-like from G.
Okay.
And if you were to, so if you already knew where R was, then you should just move G all the way out to being null from R. But if you don't know where R is, then you should pick G for a condition that's general. You should pick G to be the biggest region you can that doesn't eliminate any region R. So let's look at the black hole example, because this is a good one. So in the black hole example, suppose we were guessing that our island was going to show up on the inside. So we knew our island was going to show up inside the black hole. So in this example, you should pick region G to be here. Because that'll guarantee that it's space-like separated from whatever R you might want to consider when you apply the island rule.
Okay.
And we're going to see a similar situation in cosmology. Okay, so to sort of recap the conditions, there's 3 conditions on islands. First of all, I violates the Beckenstein bound. Secondly, I is quantum normal. And third, G is quantum normal. It seems to be very difficult. This is now an experimental fact, although I can give equations to support it. It seems to be very difficult to satisfy all 3 of these simultaneously. Let me give an example. If you can easily decrease the area of a region by making it very wiggly in a null direction. This was another one of the reasons that the Busso bound was needed instead of the Beckenstein bound. So by making a region, the boundary of a region, very wiggly in a null direction, you can always violate the Beckenstein bound. Just in my office here, I can violate the Beckenstein bound by picking a null wiggle. But when you do that, you make it impossible to be quantum normal, because the top of a wiggle has one sign for the derivatives, and the bottom of the wiggle has the other sign. So you make it impossible to do that. So it's generally true that these conditions are sort of in tension with each other, and they don't want to all be solved. You have to do something very special to be able to solve, to be able to satisfy all 3 conditions. In fact, in FRW, we'll see that these conditions are sufficient to produce an island. They're always necessary, but in FRW, they're also sufficient. So now let me move on to the cosmology examples and applications. Ignore the right half of the picture for a minute. So we're just studying FRW cosmology in 4 dimensions. So we have a 4-dimensional gravity coupled to a matter sector, which I'm going to assume to be a CFT. That's in order to be able to do the calculations. I don't think I'd say it's probably not necessary. But we have 4-dimensional gravity plus a CFT. So we have an FRW cosmology. Now in FRW cosmology, the matter sector is not in a pure state. The matter sector is thermal. So we have thermal matter. And what we're going to do is we're going to purify that thermal matter by introducing a second auxiliary spacetime. So the auxiliary spacetime is a Minkowski space without gravity, just the CFT. So this one has gravity plus CFT. And this one just has the CFT. I'm assuming the number of degrees of freedom in the CFT is at least moderately large, so we could ignore the entropy of the gravitons themselves. So we have this non-gravitating auxiliary region, and we're going to use it to purify the state of the matter fields. So altogether, the model is a thermal field double state where the two sides of the thermal field double, one of them is FRW, the other one is flat. But the matter fields are in the thermal field double state, so that if we trace out the Minkowski space, then we get a thermal state in FRW. In FRW, the Einstein equations are satisfied. In the Minkowski, there's G Newton is 0, so there's no Einstein equation to satisfy there. So that's our theory. And now when we look for islands, what we have in mind is the following. Well, we want to ask whether there are regions in FRW which can be islands. So we are looking for situations where there's a region R in the auxiliary space and a region I in FRW. So you should think of the auxiliary space as being like the Hawking radiation, the evaporating black hole problem, and the cosmology as being like the black hole interior. So we're looking for islands in the gravitational region through their entanglement with the auxiliary Minkowski space. Is that clear? Questions? Okay. So now we want to apply the island rule. Here it is. To apply this rule directly, which we can do, and I'll come back to this, we have done this, but it's sort of hard. And the reason it's hard is to find islands directly, we have to calculate the entanglement entropy of I union R. So let me go back up again. We'd have to calculate the entanglement entropy of this setup where we have the thermal field double of Minkowski with FRW, and then there's matter fields. So you have to then calculate the entanglement of disjoint regions in this double space-time. That's actually doable for the terms that we need, but I don't want to do that yet because we don't have to. So first, let's apply the three conditions to our putative island I. This is much easier because it's easy to calculate the entropy of region I. The von Neumann entropy of region I, SQFT of I, is dominated by the thermal entropy. Remember that once we reduce the state into FRW, we just have a thermal state. We're just calculating the entropy of a thermal state. So that's easy. We don't need any fancy entanglement entropy technology in order to calculate that. That's just some basic cosmology formulas. And now we can apply the three conditions for radiation-dominated FRW. I won't go through the calculations. I think I've given you all the ingredients. So it's easy to calculate the area. It's easy to calculate the entropy of the thermal entropy, which is the largest contribution of the entanglement entropy. So then you just check when the inequalities are satisfied. And here's what you find. So the normal region, the quantum normal region, which actually is about the same as the classical normal region in this case. So this is the quantum normal region in a radiation-dominated FRW is the region inside the apparent horizon. It looks like this. The Beckenstein violating region is was any regions that are very large compared to the time. And if you draw that on the Penrose diagram, it ends up looking something like this. So what do I mean by this? I mean that if we draw an island like this one, then if its endpoint lies in the yellow region, the orange region, then that region I violates the Beckenstein area bound. Now, the islands have to satisfy all three conditions, and we didn't even get to condition 3 yet, but conditions 1 and 2 have no region of overlap. So there are no islands in radiation-dominated FRW. We're trivially done the calculation. We don't have to go looking and do the hard calculation. There just cannot possibly be islands in this space-time. Now let's go to another example where we will find islands. So this example is the re-collapsing FRW. The reason this seems like a good one to look at, I should add, is that this is a space-time that expands and then recollapses. It's symmetric around some point of maximal scale factor. I've given you the scale factor here. At the point of maximal expansion, the area term has zero derivative. A dot is 0 at the turning point. And so you can imagine that helping to solve the extremality conditions when you try to find extrema of the generalized entropy. And so that ends up working, but that's sort of why you might expect it. So let me draw what happens when you apply the three conditions. Here's a Penrose diagram of the recollapsing FRW. There's a big bang in early times. There's a point of maximal expansion, call that time 0. And then it recollapses to a big crunch. The Beckenstein violating region on here looks about like, so the Beckenstein violating region is the region that's big enough, basically. Okay, so Beckenstein violating looks like this. So the region has to be large enough for your island to violate the Beckenstein bound. The quantum normal region is the region inside, let's see if I can do that again, is the region inside the quantum apparent horizon, which you can just calculate, and you find it looks like this. And condition 3, just another inequality. So you calculate the inequality and find something like this. The resolution, or sorry, the conclusion of all this is that the islands have to exist in the triple overlap of these three regions. Okay, so this picture is getting a little messy, but here it is. So if there are islands, then this is where they live. We haven't yet shown that there are actually islands, but if there are any, this is the only place they could possibly be. And so this region is actually very narrow around the turning point. You can't tell from the Penrose diagram, but the proper time height of this region is only the inverse temperature scale beta. So it's really, basically it's at the turning point. There's this tiny sliver of allowed islands which sits almost exactly at the turning point. So
Tom,
islands.
can I just have a quick
Yeah.
question about this picture? So, is this are you drawing? Is this assuming an open universe, or is it, if I had a closed universe?
I assumed flat.
Flat. Okay.
Flat. So
Okay.
so if it's well, we haven't really done the others in detail. If it's closed, then it's sort of roughly speaking, it's easier to make islands in a closed universe because
I was thinking of the whole universe would only have to satisfy condition 1, right? Or I guess the other ones would be trivial.
Yeah, exactly. So if you have a closed universe, there's this option of just including everything.
Yeah.
So that makes it easier. An open universe, I imagine, makes it harder.
Actually, condition 1 is automatically satisfied for a closed. I guess all of the conditions are automatically satisfied for a closed universe. Is
That's
that
right. That's
okay.
Right. Yeah.
Okay. So that's okay. That's nice.
Yeah. Okay. Other questions? So islands can only exist in the triple overlap. I claim that in this setup, the 3 conditions are also sufficient. That is, there are islands everywhere in the triple overlap for some region R. Unfortunately, I don't know any tricks for this one. You have to actually do the calculation of the quantum extremal surfaces. That is, you have to calculate this matter entropy, and then you have to plug into the extremization formula that the generalized entropy has 0 derivative, and just find all the islands and see what happens. Since I'm almost out of time, how am I doing? Yeah, I'm almost out of time.
Tom, you should not worry too much about time. I think we're happy to have you keep talking.
Okay, I'll just keep talking then. I think it'll just be a couple minutes over. So how do we actually find the islands? Well, we have to calculate this matter entanglement. So let me draw the picture again of the situation that we're in. We have these 2 entangled universes. The matter is in a thermal field double state across the 2 entangled universes. And we want to calculate the von Neumann entropy of I union R, where I is in one universe, R is in the other. Actually, these matter entropies of I union R are generally very difficult to calculate. And I'm in higher than 2, so in 2 dimensions you can calculate them, but in higher than 2 dimensions, there's almost no case where you can calculate the matter term in the island rule. Even in the case of the black hole, the evaporating black hole, we don't know how to calculate this matter term. There's some general arguments for what kind of form it has, but since you can't actually calculate it, you can't actually find the quantum extremal surface, as far as I know, for the evaporating black hole, say in 4 dimensions. The one exception to this are these doubly holographic situations where you embed this into a one higher up holographic theory, and then you can apply Ryu-Takanagi in higher dimensions and really calculate these entropies. So this is not something. So the fact that this is hard is not something that's new to cosmology. This was already hard in the black hole case. I think in the black hole case in particular, it would be really nice to understand this term better. At least I don't feel like I understand this term. In our setup, the important contributions can be calculated mostly. Depends on exact details of where you put region R. But the important contributions to this can be calculated using some formalism that was developed previously for studying entanglement entropy in quantum quenches. So actually, if we didn't use FRW, if we just had 2 Minkowski spaces in the thermal field double state, then this is a setup that's been studied in great detail. It's like the 2 sides of the eternal black hole, and you have entanglement across the 2 sides. So there are methods for doing those calculations in holographic theories, and they're universal results, not just in holographic theories, but universal results in any quantum field theory or CFT in certain regimes. And that allows us to calculate the derivatives that we need in order to find the quantum extremal surfaces explicitly. Just to give you a sense of whether the calculation, there's a calculation there that I won't go through, but there's sort of an obvious answer, which is that, like, if I draw a region R like this in Minkowski space, then the matter entropy is minimized if I pick region I to just be its mirror image. Because entanglement is local across the thermofield double. The modes here are entangled with the modes here up to a smearing of size beta. So it's easy to understand when that entropy is minimized, and that ends up basically being enough to solve for the quantum extremal surfaces. It's more complicated than that because we also have to understand situations where they're not mirror images, but we can do good enough to do that calculation. So for an example, of an island that you get this way is, so I drew a region R, which is just some more or less randomly picked region in Minkowski space. And I want to tell you where region I is for this case. So here's what ends up happening when you do the calculations. First, you draw region R over here. That's not quite the same. This is supposed to look like the same region. So you draw region R over here, and then you sort of shine it back. You follow back to the turning point, and that's your I. The slope of this line is theory dependent. If the CFT is holographic, then this line has slope given by the entanglement, by the butterfly velocity, which controls this matter entanglement to some extent. So that's just an example where you can really do this calculation and see where the island shows up. The lesson is that no matter where we put region R, the island is always going to show up in that little sliver that we found from the three conditions. It's going to be large, it's going to be near the turning point, or basically at the turning point. I'll just make a couple comments before I conclude. One is on pure de Sitter space in higher dimensions. So you might ask, why did we go to FRW? Why didn't we just study de Sitter, which is kind of like a black hole? There's de Sitter radiation. Maybe you can find quantum extremal surfaces here. Well, I don't have anything definitive to say about pure de Sitter, but I don't think there are islands in pure de Sitter. So that's not a complete calculation that I'm describing here, but I don't think it's possible because if you pick a region like the one that's drawn here, then it never has enough entropy. The entropy in de Sitter, from the de Sitter radiation, never exceeds the area of the de Sitter horizon. And so it's impossible to use de Sitter radiation to, at least as long as the space-time is static, I think it's impossible to use de Sitter radiation to violate the Beckenstein bound. I believe it's going to be impossible to find islands, at least for simply connected regions. Maybe there's something more elaborate that one could do, but it seems to be hard to make islands in de Sitter. There was one other example that we looked at where we found islands in de Sitter, but it was a two-dimensional model where we had two-dimensional de Sitter glued to a bubble of flat space. two-dimensional de Sitter, and it was two-dimensional de Sitter in dilaton gravity. So it was in JT gravity. And two-dimensional de Sitter in dilaton gravity is more like it's because of the dilaton, it really has crunching singularities. So two-dimensional de Sitter in dilaton gravity has these regions where the dilaton goes to negative infinity. So these are singularities, really. So it's not much like de Sitter in higher dimensions. It's more like a crunch in higher dimensions. But anyway, in this two-dimensional model, if you pick a region R up in the bubble, then you can create islands that are in the crunching region. I think it would be very interesting to explore whether this is possible in higher dimensions. I don't know whether it is because I don't know how to do the calculations. They're difficult to do in higher dimensions. We have to understand the quantum effects that you get when you have bubble nucleation in higher dimensions. The one case I can imagine maybe this calculation could be done in detail are the kinds of examples that Mark has studied using holography to calculate the matter entropy. So I think that would be really interesting to push on this bubble nucleation using those methods. Let me stop there. So concluding comments, islands give us a way to apply some of the methods, at least, of ADS-CFT beyond anti-de Sitter. In particular, we can reach inside of black holes and also inside of recollapsing cosmologies. Some open questions that this raises are, what is the dictionary? How do we, well, we have this suggestion that you can encode the island, but how do you really encode the island? There's some work on this involving the PETS map and modular flow. I think this is a really interesting direction. Secondly, what does this tell us about quantum gravity? What does this tell us about gravity in the UV? What really are we supposed to conclude from all this? And third, well, I don't think it's crazy to hope that this can make contact to real cosmology, perhaps through terminal inflation. We certainly don't have that. The cosmologies that I discussed here are not realistic. The recollapsing, but these new techniques that are coming from the gravitational path integral do seem to want to tell us something about cosmology. So that I think is also a place to watch. All right, thanks a lot.
Questions for Tom?
Yeah, I guess I'll ask a question. So I guess, yeah, I was intrigued by this story, the fact that you kind of find these big bang, big crunch cosmologies to have these islands. It was kind of similar to this thing we found in this black hole microstate cosmology paper where we were, you know, looking. I'll just draw a picture for people that maybe don't remember that story well. Oh, I guess I'm not a host. Can someone enable the Mark van Ramsdonk that doesn't have a face attached to it to share screen? Uh-oh, okay.
I'm just looking for it, hold on.
Okay, sorry. Yeah, there's...
Oh, I found it.
All right.
I thought you were going to use your fancy setup with the...
Yeah, I could have used that. I guess I should have done that. Yeah, I should have just done that. But okay. There's only a small number of us here, so I'm confident that the other thing will work. Oh, sorry. Load that up. Okay. Okay. So I have to... Yeah, the pen is a lot easier, isn't it? Okay. All right. You can see that?
Yep.
Yeah. So it was, you know, we were looking at these states of a CFT on a sphere, or circle if it's 1 + 1D, and so these were constructed with the path integral. Yeah, I wouldn't even go, okay, I'm not even gonna go through all the details, but basically there's some high energy states of a CFT that are constructed using some Euclidean path integral like this with a boundary. And then these states are in the bulk, there's some black hole. And then the spatial geometry at time equals 0, using the path integral definition of the state, we sort of realized that, okay, actually there's this black hole, and then behind the horizon of the black hole, in some holographic model, you end up with this end of the world brane. And I guess in some favorable circumstances, which we think at least you can achieve in 2D, you can actually have gravity localized on this end of the world brane. And so it's kind of like, effectively, you would have it for these states, an end of the world brane, and then you sort of find that the full bulk geometry is like this. So the end of the world brane geometry is some kind of Big Bang, Big Crunch cosmology. And then in that paper, we were kind of looking at, well, when do you get, when does entanglement entropy of your original CFT probe the end of the world brane? And so we kind of found this story where, you know, if you look at a big enough region of the original CFT, then you can get an extremal surfaces that goes kind of all the way into the island, or sorry, to the end of the world brane. But in sort of the effective field theory picture, if you were thinking about gravity being localized here, then you would just describe this as some 4D cosmology. And then you would have, like we found, you have these RT surfaces, and they kind of end on certain regions of this end of the world brane, which I think are very similar to the regions you're finding in this paper.
I see. So is that a closed FRW?
Yeah, we could do closed or open. It doesn't matter. I mean,
maybe it doesn't matter that much. As long as it's not getting the whole region.
It's easy. It's actually easier to get the island. So with closed, then there are some cases where you either have to have the whole thing as the island or none of it. With open, there's always sort of, you can choose a large enough region in the original CFT. But it's very much like you said, you can only have these islands, even if, so if I look at the entanglement entropy as a function of time, like later on, they tend, well, actually now I'm not remembering the whole, there was some dimension dependence here, but at least I think in some cases it sounded very similar to what you were finding. And so I feel like this is like maybe an example, because if you were to analyze this situation using the effective field theory, then it would maybe be the same calculation or similar kind of calculation.
Yeah, that sounds quite possible. I wonder if you can do nucleating bubbles in your setup, because that's what I really would have liked to be able to do, but it was just a bit beyond.
I guess in principle, if you had the right field theory living on this end of the world brane, you could have, you know, different minima in your potential and have different bubbles. I think that's an interesting thing to investigate. But I guess I was intrigued, you know, the fact that you're sort of finding this in general, I kind of wondered if that is suggesting that this type of setup that we were doing, you know, could be how you're supposed to describe at least expanding collapsing cosmology in ADS-CFT. I don't know. I wondered what it was telling us, because you get the same result, like just without any assumptions as you get in this kind of model. And so I started to feel like maybe this is telling us that this kind of setup is how you should do things. And maybe you don't need, like, I think as you emphasized, you don't really need the original picture to be a holographic CFT.
Well, the answers that we get will depend on the details will depend on whether it's a holographic CFT or not.
Yeah, I guess so.
Not for the region where islands can be. I think, let's see if I remember correctly. Yeah, that calculation was almost completely independent of the CFT.
Like you don't need the matter to be a large N theory, right? To get your.
I think the only result that I said in this talk that depended on it being a holographic CFT was when I told you the slope of this particular line to get to the, everything else was independent of that.
Okay.
Those details.
Right.
Our setup, we can't do the, if it's a small n CFT, like one free boson.
Yeah.
Then we can't do the calculations using, we can't do the calculations of the matter entanglement. We can't even, let's see. Well, I guess we could do them, but we'd have to be more careful because the entanglement of gravitons would be a significant component there, and we'd have to redo everything.
Mm-hmm.
I guess it would be possible, though.
Yeah. Oh, I guess my computer went away. Anyways, I find it very intriguing, the story. So, somehow it's telling you that there's this subsector of your cosmological universe that you can associate with some fundamental degrees of freedom.
Yeah. Yeah. It's intriguing is the right word. I feel like we haven't quite I'm not sure where to go next with that, but
right.
Yeah.
Right. Other questions? Oh wait, I'm not the moderator. Jamie wants to know if there are other questions.
Can I ask a question?
Yep.
In the second to last slide, you were describing a CFT attached at sort of the future end of that JT gravity. And though we can't see the slide.
Right.
So do you pick the spatial slice so that the radiation region and I lie in the same spatial region?
No.
If then, what are you purifying with I?
In this case, you can pick R to be basically anywhere up in the top hat part.
Yeah.
A natural place to put it is like on square plus, like it is now.
Mm-hmm. Mm-hmm.
And whatever you do, region I will basically sit sort of up close to the singularity here.
Okay.
But it's true that, so, and this is actually almost exactly the same as the thermal field double. This is really an example of the thermal field double calculation. It's not obvious from the way it's drawn. But in fact, if I call this region 1 and these things region 2,
mm-hmm.
then the matter state in these two regions is in a thermal field double state. So we do have a thermal field double of flat with a cosmology. In this case, this is actually a hyperbolic. So this is like a hyperbolic cosmology, but it's up to a conformal factor, basically just another example of the thermal field double.
Okay, so I is still purifying. Is there to purify some?
Well, I would say that yeah, that's right, because the regions 1 and 2 are in the thermal field double state, so the the matter in region I is indeed purifying the matter in region R.
Okay. Okay, thank you.
Tom, just one question. So exactly on this slide, you have a CF, the Brockett story of Chen, Gorbenko, and Maldacena. I remember in that paper, they found regions I that were time-like separated from the region R. Do you have some perspective on those results?
No, I don't have any perspective beyond what's in their paper. I just put it on this slide because they considered the same setup. And they noted another thing that can happen here. So the islands that I told you about are there, they're extrema, but they noted this other situation you can get where the island sort of wants to show up like this, and then is actually time-like separated from R. In that case, you get you have a different interpretation.
And does this situation that they're describing satisfy all three of your conditions?
That's a good question. I think the answer is no. At least it doesn't have to, because the way the conditions were derived was by assuming that all the entanglement inequalities that are supposed to be obeyed are indeed obeyed. But in the situation like I've drawn here with the time-like separated island, you get weird features of the entanglement entropy. So I don't know if there's, I'm not sure what the answer is, but it's not obvious that the conditions would need to be obeyed here.
Does it have to do maybe with like whether you pick the Hartle-Hawking vacuum or the Page vacuum? Because like in one of them you're allowed to have Brockett wormholes, and in the other one I guess you don't.
Well, yeah, roughly speaking, the conclusion of their work was that when you see these funny time-like islands, that's actually an indication that you've missed something, missed a saddle in your calculation of the path integral, and that you should go include that other saddle, and then you'll find something reasonable. You're right that those Brockett wormholes don't show up in the Hartle-Hawking state, but I think that their perspective was that you don't really get to pick. No, you get to pick what path integral boundary conditions you like, and your ability to pick ends there. Okay, the only thing you're allowed to pick is what the boundary conditions are, and then it's up to gravity to do the rest. So I would think they were arguing that you really have to include these Page contributions.
I see.
Unless there's one last question, maybe we should all thank Tom again.